Hello, my name is Dustin Yanowski. We are going through this book, Monoidal Categories, Monoidal Category Theory. Okay, so we're up to chapter 3, which is about structures within categories. So let's just recap. Chapter 1 was kind of an introduction. Chapter 2 was lots and lots and lots and lots of examples of categories. Okay, and great. But we don't want to just think of categories as collections of objects. We want to show that there are things within those categories that have more structure. Okay, so it's not just a bunch of objects. There are certain special objects, and there are certain operations that one can do within a category, and you get out other objects from doing those operations, and that's what we're all dealing with. We're doing section 3.1, okay, which is called products and coproducts, and basically this is about the simplest example of an operation within a category. And we're going to go through it very carefully. We're going to go through it with a lot of different steps, whatever. But the main point is the ideas in this section about products and coproducts will be used all over for the rest of this chapter for sure. Namely, other types of structures also have the same type of ideas. And one of those things is called a universal property. Okay, great. So let's back up for a second and let's talk about our favorite category of all time, namely the category of sets. So let's talk about, in the category of sets, we have two sets, okay, and S is equal to X, Y, Z, and T is equal to 0, 1. Okay, then one of the things we saw is we could take the Cartesian product of the set. So let's do that. So you have S cross T, okay, and let's just remember what that is. Those are ordered pairs of elements here. So it's X, 0, Y, 0, doesn't matter what order you write them in, Z, 0, X, 1, Y, 1, Z, 1, okay, and the idea is that this set has all the information in S and it has all the information in T, okay. Now, there are two functions, okay, from S cross T. One is to S and one is to T. These functions are called projection functions. We call it, that's a Greek letter pi for projection, and here's another letter, Greek letter T, another function, pi of T, okay? And what these functions do is they forget the other information. In other words, this function from this to this forgets the T information, and this function forgets the S information. Let me just say what this is, okay? So this is 0, 1. This is X, Y, and Z, okay? And so it would take Z, 0 would go to Z over here, okay? Y, 1 would go to Y over here. X, 0 would go to there, okay? As opposed to that, this function takes an ordered pair and it outputs the 1 or 0, depending on what it is. So Y, 0 would go to 0 here with this function. Y, 1 would go to 1 here. Okay, so these two functions forget the other functions. So they're kind of integral to this product. Okay, great. Now, I want to talk about another set. So let's say we talk about another set V. And V, we're going to have different types of V's. We're going to do 3 examples of this. But let's say V doesn't equal to this whole set, but it has some of the elements. For example, it has Y, 0, it has X, 1, it has Y, 1. Okay, let's say it has those 3 elements. Okay, well, just like you can forget the information from this set to here and here, so too you can forget the information from this set. So let's see. y comma 0 will go to y over here. And that's the only thing. And x comma 1 will go to x over here, and y comma 1 will go to y over here. That's very good. Okay, but this also, so we're going to call this k sub s. Okay, so it's a function from this set V to here also. Well, guess what? There's another one here too called k sub t, and that's going to also forget that information. Okay, so let's go through it. Y comma 0 will go to 0 here. X comma 1 with this function will go to 1. Y comma 1 will go to 1. Okay, great. Now ask yourself a fundamental question. So both of them have forgetful functions to s and t. Both of them have these functions. Why is this set better than this? Okay, let me put it another way. Why does this set with its functions better than this? This also has information from both s and t. And the answer is, this has all the information from s and t. Okay, s has 1, 2, 3. T has 2 elements, so 3 times 2, this has 6 elements. 1, 2, 3, 4, 5, 6. In contrast, this has 3. 1, 2, 3. Okay, so this is somewhat better. Okay, and the answer is as follows. This is better. It's a bigger fit. It's a better fit. It has every single piece of information. And the way we write that is as follows. There's a function here. We're going to call it h. I'm going to give it another name in a second. We're going to call it h. And this function is an inclusion into here. Okay, it says, yes, this has both of information from both s and t. This has both information from s and t, but you know what? This has more information. Okay, now not only does it have such an arrow, but also these two triangles commute. Let's just go through it. Take x comma 1. That's over here going to go to x. Here it's going to go into x comma 1. Okay, it's an inclusion. Okay, and here it's going to go to x also. So this will commute and this will commute. Okay, so this is a first example of something that we're going to see a lot of, namely, this S cross T, not only does it have the structure, but it's kind of the best fitting structure. Okay, great. Now, let's look at another set, V. Okay, I'm sorry, I just want to write this another way. I'm going to write it 2 different ways. We're going to say there exists a unique H. There is only one H that makes these 2 things commute. Okay, and that's the inclusion. Okay, and another way to do it is this is also this H is gotten from these 2 functions. Okay, so we write it like that, brackets, ks, kt. So this map H depends, it's another way of writing that, it depends on both k of s and k of t, both of these functions. Okay, great, I want to talk about another set V. So how about Z is this? V is this, A, B, C, D, E. Okay? Okay, now, I don't know, A, B, C, D, E has nothing to do with X, Y, and Z, and has nothing to do with 0, 1. But you know what? There's some type of function from here to here. There are these 2 functions. Okay, so imagine for a second, and we're going to take this off, but I'm going to put it right back in a second. But imagine for a second that you have this set, A, B, C, D, and there's a function from here, and there's a function from here. So let's just give some values. For example, k sub s of A might go to y, and k sub s of B might go to z. And let's just do more. K sub t of A might equal to 0, and k sub t of B might equal to 1. Great. Okay, question. What's the relationship between this set and this set? Okay, and the answer is there might be many things. There's 6 elements here. There's 5 elements here, so there's many different maps from here to here. However, there is exactly one, okay, so let's write it like that. There exists exactly one H such that makes this commute, okay? And what should H do? Okay, so the answer is as follows. H of little a should take into account what this does and what that does. What does K of S do and what does K of T do? And the answer is, so K of A goes to Y and it goes to 0. So this should go to Y comma 0. Okay, H of B should go to, well, follow what this says and follow what this is. Okay, and so it's equal to Z comma 1. Where does Z comma 1 live? It lives in S cross T. Okay, so let's go through this. Given such a V has any amount of elements you want, could have infinite number of elements. As long as there's a function here telling where those elements go over here, telling what information it gives in S and what information it gives in T, then there's a unique function over here that commutes with this and that commutes with this. Let's just make sure it commutes. Ready? A here goes to Y comma 0, okay? And over here it's going to go to Y, okay? So Y comma 0, here it just goes to Y, so that commutes. So there's a unique map like that. And again, the proper way to describe this is this map depends, it goes from here to here, but it depends on K of S and K of T. Okay, great. So that's the second example that I want. Okay, I want to do a third example. Okay. Okay, let's just get back our information, our broad information. Okay, let's look at another example of a set V. You know what? We always wrote our ordered pairs with round brackets. What happens if we did the stupid thing of writing them with square bracket, with angle brackets? Okay, I don't know what they call brackets. So these are round parentheses. Let's say we use brackets. So we'll say V is the ordered pairs of these guys, S, and these guys. So it's going to be X comma 0 brackets. Sorry, Y comma 0 brackets, Z comma 0 brackets, comma, X comma 1 brackets, Y comma 1 brackets, Z comma 1 brackets. Okay? Now, obviously, by the way, 1, 2, 3, 4, 5, 6, there's 6 elements here. And obviously, it really doesn't make a difference whether you use round brackets or round parentheses or square or arrow brackets, whatever you want to call them. Okay? And this set will also have projection functions. So this will go to X, this will go to Y, this will go to Z, this will go to, I'm talking about this way. This will go to X, this will go to Y, this will go to Z. In terms of T, this will go to 0, 0, 0, this will go to 1, 1, 1. Very nice. Okay? Okay, but what's the relationship between this set and this set? And the answer is there's 6 to the 6 different functions here, but there's only one function that will make these two things commute. And what's that function? We'll call it H, and again, it's unique, so we write it like that. Okay, and we call it H, and basically H of, let's do Z comma 0, oops, bracket, is equal to, round bracket, Z comma 0. Okay, it takes it to the exact same thing. So not only is this, in this case, not only is this go like this, but also this is an isomorphism. This has 6 elements. Each element goes to the same element, and we can go the other way too, and so that's an isomorphism. Okay, so these are 3 ways of seeing this. The main point is, what is S cross T with these projections? Namely, there are ways of separate. This is a joining of the information. This has information. This has information. This is a joining of the information and showing how it works. And if there's any other guy there, then that also has functions, then this is the best fitting or the best way, which means there's a unique morphism from here to here such that this triangle commutes and this triangle commutes. Okay. Okay. This is called a universal property. Universal property. Okay, and the idea is as follows, that it's universal in the whole set, in the whole category. In other words, this is in the category of sets. This is an element in the category of sets. Give me any other element in the category of sets with morphisms like that, then there's a unique morphism like that. So it's universal. It goes across all possible objects with two morphisms coming out of it. Okay. So, and it's a way of defining things. We're going to see that in a second. It's a way of defining things. It's a way of saying this is important because you can define it by any other object in the category. Okay. I want to show you another place. We don't need this. I want to show you another type of thing where you might have seen this before. In even elementary school, they do this. Okay, so, and I want to make an analogy between that and this. And the idea is as follows. Take the set, a half, 2/3, 3/4, 4/5, ... Okay, basically n over n plus 1. Okay, ... Okay, here's an infinite set. Okay, and now we want GL, what is it called? GLB? Greatest lower bound. Okay, let's just write it out. Greatest lower bound. Okay, now let's just look at this set. This set obviously gets closer and closer to 1. I don't know if it ever reaches 1. Well, ... I don't know if it ever reaches 1, but it's like that. We want a lower bound for this set. In other words, give me a number that's smaller than all these numbers. Okay, and the answer is, well, 0 is smaller than all these numbers. 0.3 is smaller than all these numbers. Okay, 1 over 2.5 or 2.1 is smaller than all these numbers. Okay, okay, all these three numbers are smaller than every number here. So what we want is a lower bound. But then we want something else. What's the other thing? We want a greatest lower bound. Okay, so question. These three are examples of lower bounds, but what else is the best fitting lower bound that you can't get any better? And the answer is 1 over 2. Okay, that number is less than or equal to all these numbers. It's less than or equal to all these numbers. And if you give me any other number that's less than or equal to all these numbers, this one, these are less than this. Okay? Now, let's write that out. You ready? A half is less than or equal to, let's call this set S. Okay? That's less than or equal to S for all S member of S. Okay? And if any other Y is less than or equal to S for all S member of S, then what do we have? Y is less than or equal to x. Okay, so this is, less than or equal to a half. Okay, so a half is less than everything else. It's a lower bound, but it's the greatest lower bound. Okay, now I want to make that the same analogy as what we just saw before. So we have a set S cross T, and it has two functions to S and T. Okay, great. Okay, now there might be other sets that also have two functions to S and T. Well, guess what? There's a unique map like that. Okay, so again, this is smaller than all the others. There might be others that are smaller than all of the elements in S. Okay, and by small, I mean there's an arrow here. Well, that means Y is a smaller. Now, one of the things we saw is with partial orders or pre-orders is that we can write, these are partial numbers, are partial orders or pre-orders, total orders, whatever. But the main point is we can write this with arrows. So let's rewrite the same thing with arrows. What it says is that a half is less than S for all of that. And furthermore, if there's any other element Y, such that Y is less than S, okay, then what did we see? Then Y is less than that. You know what? We should do it more. Okay, so that's one way of doing it. I'd like to do it another way. Okay, so here's a half. Here's S, and there's a lot of S's. S, S prime. So here's another way of saying it. If there's a map from here to here, and there's a map from there to there, such that there's any other map from here to here, and here to here, so these are the two elements in S, but of course there's an infinite number of elements, then there's a unique map like this. Well, these are partial orders, so there's only unique maps, but this is the best fitting. That's the way we want to do it. Okay, so that's an analogy with something we just saw. Okay, so we had 3 different examples here. We have another example here, and I think it's time to actually make a real formal definition of what a product is. Okay, so S cross T is a product, and we're describing products, and so I'd like to tell you what a product is. So, given a category A, with 2 elements in A and B, elements or objects of A, then the product of A and B is an object A cross B. We write it like that. Okay? It's not just the product. You have to include the maps also. With maps, okay, A cross B to A, we'll call that pi of A, and A cross B to B, we'll call that pi of B, okay, and it satisfies the following requirement. Here's A cross B, and it has to A, and it has to B, and this is pi of A, and this is pi of B. Well, has its following requirement. Very important. You ready? And again, I'm not going to write it here because you're going to read it in the book, but just want to go through it. For any object C with any morphism like this, call that K of A. And any morphism like that, call that K of B. Okay? There is a unique, okay? There exists a unique H, okay, from here to here, such that this triangle commutes, and that's it. Okay, now, since this H depends on what maps you choose, there might be other maps that do this also, what maps you choose, so we're going to write it also like this, K of A, comma, K of B. Okay, so that's a product. Okay, so we saw product in sets. Product in sets is the Cartesian product of sets, which we saw many times before. Okay, and now let's look at other places where we have a product. So for example, a partial order. Okay, a partial order, you might have an element P and you might have an element Q. Okay, and you want the product of it. Okay, so the product is written like that. P and Q. P meet Q. Let's just go through what the properties of this. Okay, P and Q is less than P. Okay, that's what it means to be in a partial order in terms of categories, in terms of arrows. P and Q is also less than Q. Okay, and if there's any other objects, I just want to see what I called it, C. Okay, if there's any other object such that C is less than P, C is less than Q, then C is less than P and Q. Okay, let's just write it. So this is the way in categories, but let's just write it in terms of partial orders. P and Q is less than or equal to P. P and Q is less than or equal to Q. If C is less than or equal to P, and C is less than, C is less than or equal to Q, then C is less than or equal to P and Q. Okay, that takes care of that. Great. So this is in any partial order function. In any partial order, sorry. Okay, let's do another example. We had computable functions. Okay. Okay, let's just remember what these are. The objects are different types. Types to be thought of as things that information comes and goes from different types. The morphisms are functions between these sets of data such that can be done by any computer. So these are computable functions. In particular, you might have a type of type 1, and you might have a type of type 2. Well, guess what? You then have a type of type 1 cross type 2. Okay? And these have projections. So if I have data that has two aspects of it, two parts of it, I can forget one part and I forget another part. Okay? And so this has that. Okay? I don't want to write the entire universal property, but basically you have functions like that. Let's just do it. Let's say you have another type 3, okay, and you have some function that brings information of this type. You have a computable function that takes information of this type to here and information from this type to here. Well, then there's the same function, then there is a unique function that takes that information that's done by this computable function and that computable function and gives out H, which is equal to F comma G. Okay, so that's for computable functions, it works. Okay, so that's in the category of computable functions. Let's see some more other examples. So we had the category of graphs. Okay, what's the category of graphs? The objects are graphs. The morphisms are graph homomorphisms, which we spend time. Those are morphisms that move objects to objects and morphisms to morphisms. And guess what? If we have a graph G and we have a graph H, then we can have the product of G and H. Okay, the objects of this are pairs of objects from here and here. The morphisms, there's a morphism only if there's a morphism here and a morphism here. Okay, and guess what? They have graph homomorphisms that are projections. Projections. So pi of G, pi of H. Okay, and if you have any other graph, let's call it capital K, okay, with morphisms here, then there's a graph homomorphism like that. Okay, so graphs have products. Okay, great. Okay, so again, so we saw examples from the category of sets, we saw examples from numbers, we saw examples from partial orders. We saw examples from computable functions. We saw examples from graphs. Okay, and so we have to do a little bit. First of all, let's do a little talking. You ready? This is called a universal property. Okay, within any category, it happens if it satisfies this property for all other maps, for all other objects and maps in that category. Okay, so that's a universal property. Okay. Now, certain categories might have products. We saw a lot of examples that have. There are certain categories that don't have products. There are certain categories that have sometimes products. For some, give me two objects, yes, this will satisfy it. But for other two objects, it doesn't satisfy it. So we don't say that that category has products. We say sometimes it has products. Okay? And sometimes we're going to say the product doesn't exist. Okay, if a category has products, then it has for all of them, but if not, not. Okay, so we have to go through that. Okay, great. Now, do we say a product exists, or do we say the product exists? Do we say a product exists, or the product exists? Or do we talk about a product or the product? And the answer is we talk a product. Okay, and the reason is as follows. Let's say you have A, an object of the category. So you have a category A and you have an object A. Okay? Then you have another object B. Okay? And let's say I say that C is the product of these two things. What does that mean? That there's morphisms from here to here and it satisfies the universal property. Great. Let's say I have another object here. Okay? And it also satisfies the universal property. Okay? Well, by the universal property, since this is a product, there's a morphism like this. Okay? Also, from the fact that this is a product, means that there's a morphism like this, and you have to go through the book, shows that these two things are inverses of each other, and so let's just write it without the two arrows. Let's just write it as one arrow. Okay, there's a map from here to here, and it's an isomorphism. Okay, and it's unique, and these two triangles commute, both this way and that way. These two triangles commute. Okay, so there can be more than one product for two elements here, for two objects here, A and B. There can be more. In fact, there usually is. Okay? But they're related to each other in a way that we talked about before, namely, they're unique. The product is unique up to a unique homomorphism. I'm sorry, isomorphism. They're unique up to a unique isomorphism. Okay? So again, yes, products are important, but there's not one of them. There could be many of them. We saw this before when we talked about terminal objects in the category of sets. There are many terminal objects in the category of sets, every one object category, but they're related by a unique isomorphism. So too, these are related by a unique isomorphism. Okay, great. Next. I want to write the product in a special way. Hold on. Okay, there's another way to define the product. We gave a definition. I just want to put it in another way. Okay, look what it said. It said for every two maps. For every what's a product? It's an object A cross B with two maps like this and like this. Okay, such that for any other object and for any maps like this with two objects like this, there is a unique map like that. Okay? I want to write it another way. It says as follows. Hom of C comma A cross ham of C comma B. What does that say? These are maps from here to here and from here to here. C to A, C to B. Okay? Okay. For any two maps like that, you can also look at a map from C to A cross B. Okay? That's a map from C to A cross B. Okay. Now, the point is that there's two maps between these two sets. These are Ham sets. So this is the set of maps from here to here. This is the set of maps from here to here. This is the set of maps from here to here. Okay, so take those two maps, okay, take a map here, let's not call it F, let's call it K sub A, and take a map here, K sub B. Well, then you can put it over here. I'm going to write it like that. K sub A, comma, K sub B. Okay? Okay, so that explains how this map works. Okay, how about this map? Well, watch this. If I give you a map H, so H goes here, then I follow along H composed pi of A. So how do we write that? We write H composed pi of A. That gives you a map H composed pi of A. That gives you from C to A. Okay, and also H composed pi of B. Okay, so this map is composed pi of A, comma, composed pi of B. I'll put a dash there. Okay. Anyways, turns out these two maps are inverse of each other. In other words, they're isomorphic. Now, we need another requirement. I didn't say that this makes these things commute. Okay, that other requirement is called naturality. Okay, naturality. And we'll see that later on in section 4.2. I need the notion of a natural transformation to talk about this. But meanwhile, we get an intuition. These two sets, the set of morphisms from here and here to the set of morphisms from here, are isomorphic. Okay, now what we can do is make a definition using this. Okay, and we say as follows. So we make the definition. We say as follows. A cross B is a product of A and B, if and only if, okay, for all C, we have the following thing. Ham of C, this is within the category A, so this Ham set is within the category A. Ham of C, A cross B, whatever that is an object, so we have that object, okay, is isomorphic, we have to use the word natural also, to Ham of A of C comma A cross Ham of, in the category of A, of C comma B. Okay, so we take that as a definition also. Okay, and in the book we do a few examples of just looking at it from this point of view. In particular, we could talk about the category of topological spaces. Okay, so given one topological space with a topology, given another topological space with a topology, okay, we could talk about the product of them. Okay, and let me tell you what the product is. It's T cross T prime. That's the set of objects. And I don't know, we'll call this alpha. No, we shouldn't call it alpha. We should call it, I don't know. Think of some Greek letter. We should call it, we'll call it tau. Okay, and tau is called the product topology, and it shows how the open sets here are related to the open sets here. It's not important for us, and we're not going to go through it. Another example that we do in the book is the category of groups. Okay, so given a group with an identity, with an inverse, okay, and another group, G prime, with another identity, with another inverse, we'll do this with a square bracket, okay, then you can form another group, okay, and the objects are G cross G prime. The identity is E comma E prime. Okay, so the objects are pairs of objects, one object from here, and the inverse is pairs of inverses. So, I don't know, x minus 1 comma x minus 1, something like that. Okay. Okay, anyways, main point is that to this, you have to show that the homomorphisms to this group, from this group to this group is, that the map from this, so this is a set, this is a set, the map from this to this set to this set is a group homomorphism. So too you have G prime, comma E prime, comma square bracket minus 1. You have to make sure that this homomorphism works. And again, for any other group with any other, I don't know, twiddle, other operations, if you have a group homomorphism like this and a group homomorphism like this, then there's a unique group homomorphism like that. Okay, so main point is, here's different context where the same definition defines different objects. Okay, so this is the power of category theory. We made one definition of what is a product in a category, and we were able to apply it to groups, to computable functions, to graphs, etc., etc. That's a shocking thing. Okay, one idea gets used across the entire spectrum of any type of structure. That's a very nice thing. Okay, so now we're going to do some more things with this product. We're not going to talk about within a particular category, but we're going to talk about more things like that. So let's do it. You ready? Take an object A. Take another object A. Okay, we can form the product A cross A with itself. That's very nice. Okay, and this has a projection function, and it has another projection function. In fact, that's the same morphism. Those are the same objects, so why not? They're the same morphism. Okay, now take the object A. Okay, and look at the identity morphism from here to here. And look at the identity morphism from here to here. Okay, now, from the fact that this is a product, means that there's a morphism here. And I already know what to call this morphism. I call it identity, comma, identity. Okay? Okay, but we have another name for this, and this is called the diagonal. Okay, there's a unique map like that. So, again, given the fact that a category has a product for any objects, so in particular it has a product over here, and so we can form this. Let's look in the category of sets what this is. So you have a set S, you have S cross S, okay, and you have these projection functions. So this basically takes pairs of elements, and guess what? Take the identity here, okay, and you have the diagonal. What does the diagonal do? Diagonal of a little element S, okay, is equal to the pair of it. So it takes anything to itself. We're going to see this very much in section 3.4, where we talk about things related to itself called self-referential paradoxes. We're going to use this. So this is called the diagonal morphism. I'm not going to write it. The diagonal morphism. Okay, great. And again, it happens. It's a fact for any product. Okay, great. Let's do another thing. Ready? Let's say you have an object A, and you have an object B, and you have an object A prime, and you have an object B prime. And let's say products exists for these two things. I'm going to write the products flat with it, A cross B, and we have projections, P of A, and projections, P of B. And we have A prime, comma, cross B prime, and it has a projection here and a projection here. Okay, great. Now, let's say we have a morphism from here to here. We'll call it F, from A to A prime. And we have a morphism from B to B prime. We'll call it G. Okay, great. So far, nothing strange. We just have two products. Okay, but we don't even need that. The main point is, this is a product, which means what? If you have any morphism till here, and any morphism to here, then where it starts ends up there. So let's do this. You ready? Start here. Follow this and this. That's a morphism from here to here. Then follow this from this. That's a morphism from here to here. Okay, good. You have two morphisms. Now, this is a product. Therefore, there is a unique morphism like this. Okay? And I'll tell you what the name of this morphism is. You ready? It's, let's work it out. So this is pi A composed with F, that's that, comma, pi B, that's that guy. Oops, I forgot to put names here. This is pi A prime, this is pi A B prime. Okay, so this is pi B composed with G. That's what this morphism is. Okay, but we're going to give it a different name. We're going to call it F cross G. Okay, and the way to think of it, by the way, we saw something similar to this when we were dealing with sets, namely if you have a morphism of set functions and another morphism of set functions, you can do them in parallel. That's the way to think of this. You're doing F and G in parallel. So what it does is, it takes, you have a little guy, you have something in A, you do F of it. You have something in B, you do B of it. You do G of it. Okay, so that's a definition of what this function is. Okay, very nice. We're going to see this in a few minutes also. Okay, great. Okay, now what we saw is we have an operation on maps, K of A, K of B. That gives you another map. If you have a map K of A and you have another map, then you take the bracket of it and it goes like that. We have another operation called composition. Well, I want to call it composition of that. What do I want to call it? I want to call it composition of H, right? Okay. So let me show you what this is. Let me show you what this is about. This is how this bracket gets along with composition. Again, so you might have two maps and you compose them. You might have two maps of the appropriate source and target, and you could take the bracket of them. Okay, so these are two operations on the set of maps in our category. So let's see how it works. Let's say you have an object A, and you have an object B, and you have a product, A cross B. Okay, this is pi A, this is pi B. Okay, now you have an object C. Okay, and you have a map like that, C to A, C to B. We'll call this KA, and we'll call this KB. Okay, then, by the fact that this is a product, shows you that this is Ka composed, comma, Kb. Okay, fine. Sounds good. Ready? But you can also have an object D. Okay, and D Oops. Sorry, I want to follow the book so that we don't get confused. Okay, so the book calls this F and G. Okay, so this is F bracket G. Okay, great. Now we have another map H from here to there. Okay, so this is that bracket operation. This is this. Now we have two maps. Okay, I'm sorry, I'm going to do it slightly different than the book. I'm going to do it like this. Okay, by the way, we can compose this with this, and we get H composed with G. We can compose this with this, and we get H composed with F. Okay, now I want to describe two maps. Okay, one map is, whoops, and this doesn't work. Maybe this works. Okay, this is H composed F comma G. Okay, let's write it over here. H composed F comma G. Okay, and the other map, we also have another map. Namely, D is an object in the category, A cross B is a product, and D has a map, F composed G, and G composed B. Therefore, since D is an object, by the universal property of this, there's a map. And the map goes as follows. The map is over here, and it should be called, ready, F composed H, that's this guy, comma, G composed H. Okay. Now, turns out there's a unique map from here to here, which means that these two ways of describing, such that everything commutes, which means that these two maps are really the same map. And so we have the following property. F composed H, comma, G composed H. Okay. So we had two operations, bracket, composition. Okay. And what we're trying to show is that they satisfy this requirement. So this is how the two operations get along with each other. It's very nice. Okay? Okay, we're going to use this over and over. Over and over and over. Okay, let's talk about another topic. I'm just going to mention this, but the book goes through a lot of this. When I do this, okay, so product A, projection on A. So you know what that is. That's coming from A cross B, and that's going to A. Okay, great. Now, let's say I had another object, A cross C, and A and C. Great. And there's also a projection map here. What should we call this projection map? Also A. Okay, now this is not good because I called this map the same as this map, but you know what? They're different maps because this the source of this is A cross B, so the source of this is A cross C. So I was being a little bit inexact when I called this pi of A and pi of B. What we should really call this is pi of A, B. And what we should really call this is pi of A, C. Okay, that's being a little bit more exact. See, I didn't need it when I was just writing things because you could see where it's coming from. You can see this is coming from A cross B. You can see this is coming from A cross C. But we're going to need it in a few minutes. Okay, and now there's an entire, I'll call it a calculus, complicated calculus about such maps and how they compose. Let me give you an example. Pi of A, B, C. So let me show you what that is. That's A cross B cross C. We'll see what this means in a second. This has a projection onto BC. You can compose that. So this has a projection onto BC. You can compose that with pi of BC. This takes as input B cross C, and you have a projection onto B. Okay? Okay. Anyways, now we can do other things also. We can do other things also, like pi of A, B, C, and just output a B. Okay. So we do this. Anyways, the book goes through all these different things. We're going to use this a little bit later on in chapter 5 when we talk about these products and how they work. We're going to use this essentially, but there's a whole lingo that you have to get with the notation. Okay, now, great. So we have to do this with all these different things. Okay, great. Now I want to show you one more. So this is a calculus of projection functions, and there's a lot, it gets a little bit technical, and you have to keep track of the superscripts, where the sources of these things are, and where the subscripts are, and they work out very nicely. Okay, great. Now let's take that other thing that we had with the composition and the bracket, and let's extend it a little bit. Okay, so imagine for a second you have an object A, and you have an object A prime, and you have an object A double prime, and you have an object B, and you have an object B prime, and you have an object B double prime. And let's say your category is nice and it has products. So you have products, and you have projection functions, and you have a product here, and you have a projection function, and you have a product here, and you have a projection function. Okay, great. Now, let's say you have a map here, F, and you have a map here, F prime. Okay, and you have a map here, G, and you have a map here, G prime. Okay. Now, we saw before that you can call this map from here to here. Let's go through it slowly. This is a product, and therefore you have maps like this and like this. Therefore, there is a map here. We had a special name for it, F cross G. Okay. So too, this is a product, and you have a map from here to here, and you have a map from here to here, and therefore, since there are two maps to this element, you have a map here, and we should call it after this and this. This is the way we learned how to do it 10 minutes ago, F prime cross G prime. Very nice, okay? Now, going from here to here, what you can do is you can follow it across as this. And what is this? This is parallel processing sequentially followed by another parallel processing. I want to call this like that. Hold on. I want to call this like this. This goes from here to here, and we should call this as follows. F cross G followed by, parentheses, F prime cross G prime, parentheses. Okay, great. But guess what? There's another thing that we can do. Let's see if this blue works. Okay, there's another thing we can do. Let me show you what this other thing is. Okay, it goes as follows. Okay, you ready? Okay, this is a product. Okay, and there's a map from here, not from here, but from here till here. And there's a map from here till here. Okay. Okay, so what should we call this? I'm sorry, what should we call this product? Let's do the blue. So the blue follows from here till here. Oops. Let's take that off. That doesn't work, sorry. What should we call this map that basically follows this from here to here? Okay, and follows this from here to here. So it's a map from here to here and here. Okay, this one is going to be called G composed G prime. This one is going to be called F composed F prime. Okay, and what is this? It follows the product, the projection, and then follows this map. Follows the projection, follows this map. So we should call this as follows. Ready? F prime composed F, comma, G prime composed G. Close. Okay. Okay. Now, what is that? Well, this is parallel processing of F composed F prime and G composed G prime. Sorry, I made a mistake. This is totally wrong. Okay, sorry, made a mistake. This is cross that. Let's take that off, take that off. Okay, so this is the parallel processing of the composition of maps and the composition of maps. Let's go through this again. This is the composition of parallel processing followed by parallel processing. This is the parallel processing of composition and composition. Okay, but let's go through this. Main point is both of these, all the squares commute. Okay, but main point, this commutes, everything commutes over here. There's only one map from here to here, which means that these two maps are actually equal to each other. Okay, let's write that up as a rule. Okay, so we're going to write it over here. Ready? F prime cross, I'm doing this, G prime composed with F cross G is equal to, now we're doing this one, F prime compose F cross G prime compose G. Okay. Now I'm just going to restate it again. Composition of two parallel processes, parallel processes of two compositions. And the main point is, question, how are you doing these four maps? Well, you can do them as a composition, and this is a composition, and so you're doing these two compositions and you're doing them parallel. Or another way of doing it is look at F and G, do them in parallel, then compose that, look at these two, and do those in parallel. Main point is you're going to have this thing is going to show up. Okay? And this is called the interchange law. Okay, does it have a name? No, interchange law. And it shows up over and over and over. Okay, main point is you have two operations working on morphisms, and they satisfy, there are homomorphisms within each other. By the way, here's a trick to make sure that you didn't make a mistake. There's an F prime and a G over here. There's an F prime and a G over here. Those are the same. What swaps is these two operations and this operation. So here you have the two operations inside the parentheses, the product inside. You have the zero over here. Here you have the composition over here and the product over here. Okay, great. Okay, so this will arise over and over in many different contexts, many different places. But the underlying rule is whenever you have a set of things and you have two operations working on them, if they respect each other, they're going to respect something along that lines. Okay, so let's just talk about a collection S, and you have two operations, plus and times. I don't care what we're talking about. We're not clear what we're talking about. It doesn't matter. But the main point is, let me just see what letters I used here. This is in A's, B. Okay. The main point is as follows. Follow A times. Okay. So if you have four objects, A, B, C, D, and this is a times, and this is a times, and this is a plus. Okay. Again, I'm not talking about what operations we have, but we're going to see this over and over and over throughout the book. And I'm always going to point back to this interchange law. Well, there's another thing you can do with these four objects, namely A, okay, now I have to be careful, C, B, D, okay, and we can do it like this. A plus C, B plus D, parentheses, 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 and this is times. Okay, notice they both start with an A, they both end with a D, the C and the B switches. Okay, the fact that these two are equal is called an interchange law, and what it means is that these two homomorphisms that take two things and bring it into one, okay, these two operations that take two things and bring it into one respect each other. So this is going to show up over and over and over again. Okay, some more things to do here. Let me erase the board. Okay, next thing. And this is going to be very important for coherence theory. And so this is as follows. Let's say you have three elements. So if you have two elements, you can get the product for two elements, no problem. Okay, well, but what happens if you have three elements? Well, just like adding, how do you add three numbers? There's two ways of adding three numbers. Turns out that you get the same answer, but here you don't necessarily get the same answer. So if you have three elements in your category and there are products, then there are two different ways of multiplying them. So you could take this product, okay, and then once you have the product of B and C, you have an object called B cross C, and then you have another object, then you A, and then you multiply them. But you could also do it the other way. You could have A cross B, okay, and then cross C, okay. And in many categories, these are actually equal to each other, okay, but in many categories they're not. But one thing for sure, there's an isomorphism in between them, okay. Now, I go through, so there's an isomorphism. I go through how this isomorphism is constructed in the book, but I just want to mention a little bit how it works, okay, in terms of those projection maps, okay, and you can actually see it here very clearly, okay. So the idea is as follows. Alpha is okay, the output of alpha is going to be something in here, and the way to look at it is as follows. You have the projection, but you have to keep in mind where the projection is coming from, of A, B, C. That's the source of the projection, and we're going to output A over here, okay, and then comma pi B of A, B, C, that's this guy, okay, bracket, and then that's in parentheses, comma, now we're within another bracket, pi of A, B, C, In other words, this is the input, and we output C. So you can actually see what this alpha is doing. Basically, by the way, this is not really clear. This is a composition of two things, because you can only really output A or BC. But if you output BC, then you can output again. You can do another composition and output C also. So you get this way of looking at what this does. So basically, this takes a guy over here and it outputs a guy over here. Let's just do the other map, which I call alpha prime. And so alpha prime goes the other way, and it's exactly the way you think it is. You just have to invert the source and targets. Okay, and so it goes as follows. This is going to be pi. This is going to take something from here, so that's A, B with a C afterwards, okay? And you're going to output A, that's that guy, comma, pi, A, B with a C afterwards, and output B. Whoops. Sorry, no, that's wrong. Okay, comma, pi, same source, A, B, C, then A, B, C, and output C. Okay, anyways, and it turns out that if you go this way and this way, you have this composition of these brackets and pies, and you have to follow that calculus of projection functions, and you get the identity, okay? And I can show you what the identity will look like. We can work out what the identity, let's say over here is. So the identity of this is, let's see, it's going to be this. Okay, this is pi of A, B, C, of A, pi of B, comma, pi of C. Okay, and so this is A, B, C, and this is also that was. Okay, pi of A, B, C, that's that, C. Bracket. Okay, anyways, main point is this composition here is the identity over here, the composition here is the identity over here. Alpha and alpha prime are both isomorphisms. Very nice. Let's see what this has to do with a real case. Okay, and so always we start with set. Okay, so given three sets, S, T, and U, we can do that, or we can do this. Okay, and there's an alpha in between them, kind of. Okay, and the main point is, ready? Alpha, what's a typical element here? A typical element here will be a pair of objects, because this is what it is. So it's little s, comma, oh, and what's a typical element here? It's a pair of objects. Okay. Okay, and the output will be a pair of objects here, and the output will be, ready? Little s, comma, t, comma, u. Okay, so these are elements of the sets S, T, and U. Okay, so basically you're moving the brackets, you're moving the ordered pairs made out of parentheses, so you're moving the parentheses from this way to this way. Okay, one more important morphism that we had, so let's just remember, we had the diagonal morphism. Okay, whenever there's a product, there's a diagonal morphism. We had hold on. We had the diagonal morphism. Okay, anyways, so along the same lines, we have something called the braiding morphism. And it goes as follows. Take A to B, okay? Then you have A cross B. And it goes like this, and it goes like this. We're going to call this P, pi A. I'm going to put in specifically what the source is. So this is AB. And this is pi, although you can see it right here, so you don't need it, but I'll show you why you need it in a second. AB, and this is B. Great. Now let's do something else. Let's look at B cross A. Okay, and let's look at this morphism. Pi, output is A, but now BA. Okay, and this is pi, output is B, but it comes from BA. Okay, now from the fact that, this is a product, and you have of these two elements, and you have another morphism, you have another object with morphism going to these two elements, that means that there's a unique morphism like this, making this commute. Okay, this unique morphism is called BR for braiding. You're kind of swapping them, so you're braiding them. You'll see this later on. But let's just be very formal with what it is. It's pi of A, BA, comma, pi of B, BA, bracket. Okay? Okay, and it turns out this is an isomorphism also, and you can show it by doing this. Projections, and you have, this will be called BR inverse. But you have to show it. You have to show there's work to be done. And again, the main point is that all these triangles commute and things work out very nice. Okay, now so that's the end of what we're dealing with products. So let's just go through it. A product is an operation. You take two elements, you get a third element, okay, or you get the same element, or you get another element, okay. And what we saw is there's a lot of different structure that comes with a product. Namely, it's associative up to an isomorphism. There's a diagonal map. There's this braiding map. There's lots of different things. Okay, great. Now we have the concept of duality, and this shows up all over category theory, and you're going to see it makes things much easier. The idea is as follows. Whenever you have a theorem about something in a category, okay, if you invert the arrows, you change the direction of the arrows, you get another theorem. Okay, now we saw this already. Okay, because we talked about initial objects in a category. What's an initial object? It's an object which has a morphism to every other object in the category. Well, we also have a terminal object. What's a terminal object? Well, if you change around the direction of those arrows, you have a terminal object. Okay, so category theory comes with a built-in mirror. Whenever you have a concept, if you change around the arrows, you have another concept. Whenever you have a theorem, now it doesn't always work. There's subtleties. You have to be careful. Okay. I don't have to tell you what doesn't work, okay? But a lot of times things do work, and this is something we have, okay? And the idea is as follows. Whenever you have a concept or a theorem or something in the category theory, you can think of the other way, and you get out what's called coex. Okay, so this is a totally new concept when we deal with coex. Okay, so you add the co, and you get the other way around. Great. So let's go through it. We had a product. We just spent an hour and a half talking about products and all those things. Guess what? Now we talk about coproducts. Okay? Coproducts are another operation that you can do on elements in a category. Okay? And this other operation comes from this product operation, but with the arrows inverted. Okay, so let's talk about it. Ready? Let's do it. Okay, there's a reason why I'm making my diagrams the way I do, and you'll see it next section, but other people don't do it like that. So, given two objects, I'm sorry, let's talk about it in the category of sets. Okay, because we like sets. So before we give a formal definition, let's talk about it in the category of sets. So let's take our two favorite sets. We have the set S of X, Y, and Z. You have the set T of 0 and 1. Okay, well then I can form the disjoint union of S and T, which is equal to those things in here or in here. There's nothing the same here, so there's no overlap, so it's the union. So this becomes X, Y, Z, 0, 1. Okay, great. Okay, now what I want to do is I want to show what universal properties this has, because we define things by their universal properties. So given the set S, given the set T, we can invent, there's another set called the disjoint union of S and T. Okay, and beforehand we had projection maps. That's what products were based on. Now we have inclusion maps. So I'm going to call this INC for include S-T. And in fact, I'm going to make a little hook on there to show you that it's an inclusion map. And we'll have an inclusion map here of T. Okay, so main particular thing. S, the set S is a subset of this. The set T is a subset of this. Great. Okay. But now I'd like to look at another set, V. And we're going to have a few of these, and we're going to see what we have. Okay? So here's another set. Ready? V is equal to not just X, Y, it's also equal to W, X, Y, P, R, Z, 0, 1, 2, 3, 0 prime, something like that. That's a big set. Okay? Okay, great. Now, as you see, V has X, Y, Z, so S includes into it. So we'll make that inclusion. Okay? T has 0, 1. This also has 0, 1, so T includes into it. Make a little inclusion. Okay, great. Okay, what's the relationship between this and this? And the answer is yes, this has a lot of things in it, but in particular, it has S disjoint T in it. It has X, Y, Z, 0, 1 in it, and so this includes into this. There's a unique map that includes it. Okay, I'm sorry, we should call this K sub S. We should call this K sub T, just like we did with products, but now the maps go the other way. And we're going to call this map, we'll call it H, okay, and it's unique. Again, we'll write like that, unique, but we're going to have a different name for it also. Last time when we were dealing with products, we did it with brackets, okay, arrow brackets. Now we're going to deal with like this, and I'm going to call this square brackets K sub S, comma, K sub T. Okay? Okay, great. So it works. Okay? Let's talk about another set V that works. Okay? Another set V that has the same type of structure. And again, we did this for product. I showed you 3 different V's of how it works. But the idea is as follows, is this satisfies some requirement. S includes into it, T includes into it. And it satisfies it the best. It's the best fitting. That means if there's any other object that fits into it, this one fits into it the best. Okay? And by the best means there's a unique morphism going the other way. Okay, let's do another one. How about this? V is equal to A, B, C, D, E. Okay? A, B, C, D, E. Nothing to do with the set S, nothing to do with the set T. Nothing to do here, okay? Okay, but here's what it says. Now I'm erasing all these inclusion maps because, you know what? S and T do not include into here, okay? They are not inclusion maps here. Yes, S includes into S disjoint union T, T includes into that, but these, the K of S and K of T are not inclusions because S has X, Y, and Z. There's no X, Y, and Z here. T has 0, 1, there's no 0, 1 here. So these are just arbitrary functions, okay? And you can say as follows, K sub S of X is equal to, I don't know, D, okay? And K sub T of 1 is equal to, I don't know, B. Okay? The main point, these guys, these two maps give values for here. Okay, great. Now, what does that tell us about this? What's the relationship between this disjoint union and V? And the answer is, you know what? K of S gave values for this. K of T gave values in here for the elements of T. Well, there's a map here called H, which gives the same values on it. So H of X is equal to D. H of 1 is equal to B. Okay, it's going to do the same thing that K of S does and K of T does. So in some sense, H takes the information from K, from this K and this K, and it does the same thing. So that's a very nice thing. Okay, and there's only one map that does that, that keeps all the information. Okay, so again, the way to think of this is S disjoint T has this information and that information. Okay, and it uses it in a universal way. It uses it like that. Okay, great. Let's do one more V. How about this? Let's say S disjoint T has all 5 of those elements, and let's say V has different elements: X prime, Y prime, Z prime, 0 prime, 1 prime. Okay? Totally different elements. Now again, this is not an inclusion, this is not an inclusion. X, Y, Z is not X, Y prime times Y prime times Z prime. They're not. However, there is a map from here to here, thinking of X going to X prime, Y going to Y prime, 0 going to 0 prime, 1 going to 1 prime, etc., etc. Anyways, and there will be a map like this. And it'll turn out that in this case, that map is an isomorphism. Okay? This set V is isomorphic to this. Not equal, but they're isomorphic. Okay, so here's just 3 examples in the category of sets which show you this universal property. That's the main point. We want to show you this universal property. Let's just state the universal property. Okay? If you have a set S and T, and they will include into the disjoint union, okay, such that if there's any other set and there's any 2 other maps, there will be a unique map like this, such that this triangle commutes and this triangle commutes. Okay, let's write it now for an arbitrary category. Okay, let's not just talk about sets. When we do this over and over, we look at what we learned about sets. We look at what we learned about sets and we apply it for other places. So let's do it. If you have an object A and you have an object B, then there's an object, sometimes there's an object. If the category has coproducts, or a coproduct is an object like that, that's an object. There's a map like this, which we call Inc A, and there's a map like this, which we call Inc for inclusion B, and this satisfies the following requirement. For any object C, for any map K sub A, for any map K sub B, there is a unique map H, okay, which we call K sub A comma K sub B, Okay, that makes these two triangles commute. That makes this a coproduct. Okay, great. Okay, and again, the way to think of it is this fits in, and it's the best fitting thing. It's the best fitting thing. If anything else fits in, then this fits in, shows that it fits. This extra arrow, this unique arrow, shows that it fits. Okay, now, when we did product, we did an analogy with this, okay, and we did it with greatest lower bound. Guess what? We're going to do another analogy with the least upper bound. Okay, and we're going to use almost the same set. 1 over 2, 2 over 3, 3 over 4, n over n plus 1, and, okay, I go on to 1. Although, I don't know why I did that. We don't really need 1, but that's fine. Okay, now we want something that's an upper bound. What is bigger than all these numbers? Okay, bigger than or equal to all these numbers, and the answer is 1. Okay, and what we could say is, if this is the set S, then every element S in this set is less than 1. Okay, we do less than, as we do with all pre-orders and partial orders, we put an arrow there. Okay, great. Now, great, but you know what else is bigger than this? The number 2 is bigger than this. The number 1.1 is bigger than this. The number 5,328 is bigger than every element in this. So we say as follows. If there's any other element, y, such that S is bigger than every S is bigger than y, okay, well then then y is bigger than this. So this is the upper bound. This shows this is an upper bound, but it's the least upper bound. In other words, any other upper bound is more than it, more than or equal to it. Okay, so we have, that has a similar feel to what we're doing here. Okay, if you want, we can even draw it the same way. And this is something we're going to see later on with limits. 1 is half is less than 1, 2/3 is less than 1, 3/4 is less than 1, this is less than 1, this is less than or equal to. And what does it say? 5,382. Half is less than that, this is less than that, this is less than that, this is less than that. Well, there's a unique map like that. 1 is less than that. So it's 1 is an upper bound, and for any other upper bound, it is the least upper bound. So that shows that. Okay. Okay, great. When I did products, I left out something, and I'd like to go back and do it, and then I'd like to show the same thing with coproducts. So again, this is part of this calculus of projection functions. So we're going to have a calculus of inclusion functions. So let's just do products again. Okay, you have A, you have B, you have A cross B, you have projection A, projection B. Okay, you have C, okay, and you have KA and KB, okay, and this map is what? Brackets, arrow brackets, KA, comma, KB, close brackets. Okay, now, again, I saw this before, but what I want to do is stress one thing, namely, if you have KA, comma, KB, okay, and you do the projection over here, PA, so that's composition, it's equal to KA. Okay, same thing this way. This bracket followed by the projection is equal to KB. So let's do it. PB, compose, KA comma KB equals KB. Okay, and the main idea is you think of this as projecting out which one of the maps you need. Okay, when you work out this calculus of projection functions, you're going to need this very much. Okay, okay, great. Let's do the same thing with coproducts. AB, a disjoint coproduct B. This includes here, this includes here, so we'll do this inclusion of A, inclusion of B, such that if there's any object C and any map KA, KB, okay, there is a unique map here, which we call, this was arrow brackets, this is square brackets, okay, square brackets of KA comma KB, okay, and now I just want to write out what this means, that this should commute and this should commute. What it means is similar to this, that if we do inclusion of A composed with KA comma KB, let's just do this, inclusion of A of KA comma KB equals KA, okay, and KA comma KB inclusion of B is equal to KB. Okay? So literally duality takes it away, makes everything, you get two for the price of one. Okay? Works very nicely. Okay, great. So that's what a coproduct is, and it has this property. What is, and we saw it in sets, the coproduct in sets is disjoint union of sets. We love that. Okay, we know what the disjoint union is, but what about in other categories? So let's look at this category. Computable function. Remember, the objects are types, the morphisms are computable functions, okay, which means functions from types to types, which a computer can write or can be done with a computer. Okay, so let's do it. You have type T1, you have type T2, so this could be reals, strings, characters, whatever. This could be reals, strings, products of them, etc., etc. Okay, so then there's another type called T1 disjoint union T2, which has the information of both these types and these types. There is definitely an inclusion function here. Okay, this, all the elements of the type here fit in here, all the elements of the type there fit in there. Okay, and if we have some type 3, okay, and we have a map from T1 to T3, and we have a map from T2 to T3, we'll call this K1, we'll call this K2, okay, then there's a unique map like this. Okay, and in terms of computers, this is very simple. What this map does is it says, oh, this has all the information both of here and here, and so if we have some object here, we're going to do whatever operation these two, whatever computable operation these two do, we do there. Okay, in computerese, this is called case operations. Let's just show you. Okay, so we're going to call this H. H of X, X is some element in here, is either equal to one of two things. It's either equal to K1 of X if X, I don't know, is in T1, you can use element size there, or K2 of X if X is in T2. Depends what type it is. But this is a case operator. It does this or this. So this shows up in computers a lot. Okay, so remember, okay, we saw what it does in product, now we see what it does in coproduct. Okay, great. Okay, this is a conditional statement, so this is very important. All right, let's go back to our definition of coproduct and see if we can write it the same way we did product. Okay, and so we get, okay, let's see, A, B, A disjoint union, A coproduct B, okay, C, dom, bum, bum, okay, so KA, KB. Okay, another way of doing this is as follows. We look at HOM of A disjoint union B going to C, okay, and it turns out that this is, well, let's first do it. Okay, this is HOM of A to C cross HOM of B to C. Okay, so give me a map from A to C. Give me a map from B to C. Well, then I'm going to get a map from A disjoint union to B to C. So that goes like this. And by the way, we know how to do this. This is, take these two maps and put them into square brackets and you get something over there. Okay? And there's another way of going this way. Okay? Okay, great. Now, when this is an isomorphism, not just an isomorphism, but we need again that word naturality, which we'll meet in section 4.3, okay, then this defines what a coproduct is. Okay, when you have such an isomorphism, this defines what a coproduct is. Okay, in the book I do a few more examples with partial orders and things like that, and you can see how what the coproduct of two partial orders are, etc. Okay, great. Again, let's milk duality for all it's worth. Let's do everything that we can for duality, using duality. So there's a lot of things that we saw. So let's just do this. You ready? You have an object A. You have an object B. You have an object A prime. You have an object B prime. Okay? You have A plus B. Okay, now the maps go this way. Okay? You have an object A, the coproduct, assuming the coproduct exists. You have an object like this and like this. Great. Now, imagine you have a function here. Let's say you have a function f here, and you have a function g here. Okay, let's go through this. Let's go through this. You ready? This is the coproduct of A and B, which means this is the coproduct of A and B, which means if any other object, if there's any other object like this, such that there's a mapping from here to here, and there's a mapping from here to here, by the coproduct, the fact that this is a coproduct, this map exists. We're going to call this H, but we're not going to call it H. What should we call it? It obviously depends on F and G. Okay. Now, in the product, when we were dealing with the product, we called that F cross G. Okay, and basically what that was, it was parallel processing. Okay, you do F on the A and you do G on the B. But now we're not dealing with the product, we're dealing with the coproduct. And so we're going to call this map F plus G. Makes sense. Okay, and what does it do, really? Well, this has the information of both A and B. This has the information of A prime and B prime. And what this does is, it does what it does on F and it does on G. So it makes sense if you're talking disjoint union. Okay, anyways, it's a very nice thing. Okay, great. Okay. Again, continuing on our, obviously we're doing this a lot quicker because we already saw this, but with the arrows the other way. So we're doing a lot of these things quickly because we saw this. So let's do it again. Okay, so now we have two operations that we have two operations that deal with morphisms in a category, namely composition of morphisms and taking the bracket of them, okay? And we get a new one. You have one map, you have another map going to the same place. You can take the coproduct of it, okay? Okay, great. So I'd like to know how they relate with each other, and the answer is as follows. Let's say you have A and B here. You have A plus B here. There's a map here. There's a map here. Nothing to do with inclusion now. That was with sets. This could be just any map. Great. Now we have an object C. We have a map here called K of A. We have a map here called K of B. Then we have a map here called square brackets K of A, comma K of B. So far, so good. Great. What happens if we have a D? Okay. And we have a map here called H. Okay. So now I have a map here and a map here. Let's go through what these maps are. This is KA composed with H. This is KB composed with H. Okay. And now, well, it's getting messy, but we have to deal with it. Okay. We'll deal with this in a second. And now we have a new map from here to here. Namely, what's that new map? Okay. This new map is bracket H, H composed KA, comma, H composed KB. Okay. But we also have this map. This followed by H. Okay. And this makes this commute, all four triangles commute. That takes time to see. Conclusion, there's two maps going from here to here, and they have, since it's a unique map, they have to satisfy it, and so we get the following fact. H of KA, comma, H of KB, bracket, equals H composed of KA, comma, KB. Okay. We saw something very, very similar with the product, okay? And the product, the H is on this side, and we show that we can compose it. Doesn't even make sense to talk about composing the H on the other side with square brackets, but that's, you have to check. Okay? So this is the way composition respects this bracket operation. Okay, great. Okay, next. And again, we're doing this double speed because we have already saw this, and so we know the concepts. Let's say you have three objects in the category, A plus, B plus C. You can do the coproduct operation like that, or you can do the coproduct operation like that, and there's an isomorphism in between them. Okay, this is called, well, for the product it's called associativity. This is also called an associative operation. Well, anyways, alpha is an isomorphism. You have to look in the book to see how alpha is defined. Also, it's going to be with brackets and projection and inclusion maps. Okay, very nice. Okay, great. Next, what happens if you take A and you do A plus A? Instead of taking two different elements, you take the same element. What happens here? So you have the inclusion here, you have an inclusion here, okay? And let's say you have the A element here, and you take this as the identity on A. And here's a nice map, identity on A. Well, by universal property of coproduct, there's a map here. Okay. Now, for the product, we call this the diagonal map. Okay. This is upside down, same identity map, but upside down, so we call this the codiagonal. I think it's also called the nebula. That's a Greek letter, but it doesn't matter. We're going to call it the codiagonal. Okay, great. Next. So we had the diagonal, now we have the codiagonal. We had the braiding operation, now we're going to have the cobraiding operation. Let's go through it. You have A and B, then you can have A plus B, include, B plus A. Okay, we have to have the same thing. So this we call inclusion. Okay, we call this inclusion of A. This is A plus B. This is, or AB. Damn, AB. This is inclusion of B. We should really write this as AB. Guess what? There's a map over here and a map over here. And this should be called inclusion of BA into, from A. This is inclusion of BA into B. And this map should be called the cobraiding. And it's an isomorphism. And you can figure out what the inverse is. And it's very nice. Okay. Okay. That's it for duality. We have one more concept to deal with, but that's it for duality. I just want to say, duality is your friend. Duality shows up all over category theory. And like I said, it's two for the price of one. Whatever idea you have to explore its co-idea and see if it's applicable, see if it's useful, and then do it. Okay, great. Now, question. Let's say you have a category that has both a product and a coproduct. Okay, we're going to see set has that. It has a coproduct and a coproduct. We're going to see computable functions has that. Okay, well, let's see what we have then. Okay, well, given three objects, A and B, we can do that, A cross B. Okay, we can also do, you have A, B, and C, you have three objects, so you can also do A cross C, and you can do the addition of that. Okay, you could do the coproduct of these. Another thing you can do is, you could do this, and then you have an object B and an object C. You take the coproduct of that, and then take the product of that. Okay? Now, in the book, I show, so let's just go through it. You have a product in your category, you have a coproduct in your category, then you can form these things. In the book, I show that there's a morphism from here to here. Okay? I don't remember, let's call it H. Okay, there's a morphism from here to here. Okay? Now, this morphism is not necessarily an isomorphism, but we know this morphism from dealing with numbers. Okay? What does this say? This says that that the product distributes over the coproduct. Okay? The product distributes over the coproduct. Okay, now at times, certain times, this in certain categories, this morphism is not only just a morphism, but it's an isomorphism. Sometimes it is. Okay, when it's an isomorphism and it satisfies some other requirement, then the category is called, you ready? A distributive category. In other words, the product and the coproduct, the product distributes over the coproduct. Okay? You have to talk about the other case also. Anyways, turns out sets is a distributive category. It's a very nice requirement to make, and sometimes it happens, and there's a whole subfield of category theory about distributive categories. Anyways, so that's the end. Let's just recap what we did. Okay, what we saw was categories are not just collections with maps, there's also structures there. We can have certain operations, and the simplest operation we can have is the product and the coproduct. Okay, and so we saw lots of different theorems about what you can do when there's a product, or what you can do when there's a coproduct, and what you can do when you have both of them. Okay, great. Let's see what we're going to go further. What we're going to do further is we're going to look at more structure that you can find within a category. Okay, other operations you can do with the morphisms of a category, and how they all interact. That's the next section. Okay, I just want to point out in two sections right now. So this is section 3.1. Then we have 3.2, 3.3. In section 3.4, we use this product and the diagonal map to get theorems from all over. It's a mini course on something called self-referential paradoxes, and we get theorems from all over just using the fact that a category has a certain product. And so we'll see that a lot. Okay, have a nice day.